Okay, now I would like to review the canonical transformation and derivation of the Hamilton-Jacobi equations, okay? So I think that many students told me that it's not very clear how to derive the Hamilton-Jacobi equations from the canonical transformations. Canonical transformation to derive the Hamilton-Jacobi equation. Okay. So this, for short, is CT, and this, for short, so HJ. Okay. So canonical transformation is like this. You transform the Hamilton is a function of Q, P, and then you transfer to the Hamilton. That's a new Hamilton, right? Oh, sorry. Which is the function of the new coordinate, that is Q, P, capital Q and capital P. And any transformation will be made by using a generating function. And we can choose the generating function of the type 1. Okay? So what is type 1 generating function? It is a function of the Q, which is the older, that's the old coordinate. And then you change this to the capital Q. And that is the G1, type 1 canonical transformations. And then you get the same thing that for this Hamilton, you have the Q dot is equal to partial H, partial P, and the P dot is minus partial H, partial Q, right? And the equations will be kept unchanged for the new Hamiltonian and new coordinate. So you have the Q dot is equal to partial K, partial P, and the P dot is minus partial K, partial Q. And also, from the derivation of the type 1, type 2, type 3, and type 4 generating functions, we have some very useful relations. The relations is like this. For the type 1 generating function, G1, that's Q, capital Q and T. We have the P, that is the old canonical momentum, right? Is equal to what? A partial G1, partial Q. That is, we have derived last time. Remember? And how to derive this relation? You know that it's very simple, right? We can just compare the coordinates for dt and dq and d capital Q. And then you get the some equations and the relations, right? Yes? Okay, good. And also, we got the capital P is equal to minus G1 minus Q. And then you got the relations of the small p and capital P relations with the small q and capital Q through the generating function of the type 1. And also you have another very important relation, that is the new Hamiltonian is equal to the summation of the old Hamiltonian plus what? The partial G1, partial T, right? So that's what you have derived last time when we compare the the equations of the old and new Hamilton relations, and you get that. Remember that? I think that you have reviewed some of the contents we have taught last time, and so I suppose that you're very familiar with that. It should be. Okay, that's these equations are important that we would like to mention here, and it should be emphasized that all the equations here are very important for us derivation of the Hamilton-Jacobi equations later. Okay? Okay, now, so you can choose many, you can have many choices of the new Hamiltonian and new coordinate, and it's up to you. You can have two flexible things that you can change, and you can keep the other two things fixed. And one of the choices of this is very simple. You can find that we can suppose that the new Hamiltonian could be like this. We can choose the 0, of course. It's very simple, right? And also we can choose the Q is equal to Q0. What is Q0? This is T0, and this is T, and so, and this is the physical path that we have taken for the systems from T0 to T. And this is a path, this is a physical path. Physical path. So for this physical path, the Q, the time-dependent function of Q should obey what? The equation that is Euler-Lagrange equation, right? Yes? Yes. That's what we have derived from the principle of the least action. And how did we derive the Euler-Lagrange equation? Do you remember that? We fixed the 2 points, these two starting and end points, the T0 and T, and then we derive the Euler-Lagrange equation, right? So we can fix the path, but we can make this point and this point to be changed. To derive the Euler-Lagrange equation, the thing that we fixed are the 2 points. We have several passes, and only one path is physical, right? We fixed the 2 points and derived only one path that is physical path. The physical paths obey the equation that is called the Euler-Lagrange equations. And also we can fix the paths and let the 2 points to be changed. And then we can get some relations. That is what we have derived last time using the delta S is equal to 0, because this thing should be satisfied no matter in what conditions. That should be satisfied. When you fix two endpoints, what do you get? You get the Euler-Lagrange equation. Right? That is d over dt partial L partial Q is equal to partial L partial Q. That is what we have derived last time. And also, you do not need to fix the two endpoints. You can fix the paths. When you fix the path, because the path has been the physical path, right? What did you get? You derive two things. The first, when the Q0 is fixed, you can get the P is equal to partial S partial Q, right? And when the Q is fixed, but the Q0 is not fixed, but the path is fixed. The path is fixed because the path is a physical path. And what can you get? You can get the P0 is equal to partial S, partial Q0. You can derive this and this. And according to these relations, what can you get? You can get that because the L dt is S, right? T0 to T. That is the definition of the action. The action is the integral of the Lagrangian over time. So from this, what can you get? You can get that the ds over dt is equal to what? L, right? That's a very simple calculus relations. You can do that when you are the freshman in the undergrad level. You can get that very easily. And what's this? ds dt, what's that? The s is a function of what? Of q and also t, right? The s is a functional of q because q is a function of t. So ds over dt is equal to partial s partial t. That's one of the terms. And then what? Partial s, partial q, and q dot. Right? Any problems? No problem. And what's this? Partial s, partial t, plus, what's this? This is this one, right? Partial s, partial q is equal to the partial l, partial q dot, and is equal to p. Okay? P, q dot. And from this, what can you get? You can get the partial s, partial t is equal to minus pq dot plus L. What's this guy? It is a minus h. It's a minus Hamiltonian. And Hamiltonian is a function of q and p and t. And what is p? P is equal to partial s, partial q. So that this is the Hamilton Jacobi equations that we derive from the very principle of the least action. We can derive this guy and this guy and this guy. And now let's turn to a canonical transformation. Let's see if it coincides with that derivations, okay? But we have already derived the same thing as three equations, P, P0, and partial S, partial T. So we got that the partial S, partial Q is P. Partial S, partial T is minus H. And so let's check. When the new Hamilton is equal to 0, and new coordinate Q, capital Q is equal to the Q0, this guy. And the capital P is equal to P0. Let's see. If these conditions are satisfied, what will happen? The thing that will happen is very simple because the K is equal to H plus partial G1 partial T. If we suppose that if we let the G1 is equal to S, and then you get that the partial S partial T is equal to minus H, that is Q, partial S partial Q. Oh, no. We have not yet derived that. We'll just leave something here. It should be the function of this. And what is the Q? The Q dot is what? Is the partial H, partial P, capital P, because the K is a constant, that is 0, so that is 0. And P dot is the partial K minus partial K, partial Q, and also equal to 0. So Q dot and P dot will be the 0, and so the capital Q and capital P will not be changed, right? And actually, we know that it's a partial Q 0, partial P is 0, and this guy is a partial P 0, partial Q is equal to 0. Yeah. And let's see. And if these two equations coincide with the derivations of that, and we can derive that the P is equal to partial G1, partial Q. So that is partial S, partial Q. And also we have the capital P. What is capital P now? That's equal to the small p0, right? That is p0. And what's that? That is the minus partial G1, partial Q. And minus partial G1, G1 is S. And what is capital Q here? It's partial. So we derive that the P0 is the same as the minus partial S partial Q0. That's the same as this one. And P, small p is equal to the partial S partial Q. That is also the same as this one. And we have this partial S partial T. And now we can write down the small p here because we have derived small p is equal to partial S partial Q. So now we have derived these equations and this equation and this equation, which are all coincide with these equations derived in another way. So this way is using the canonical transformations, using the generating functions for the type 1. And that derivation is using the principle of least action to let the path to be fixed and let the 2 points can be changed, and then we can get the relation between the small p and small p0 relations with the actions. Understand? You got what I have told you? Okay, so I would like to summarize something in maybe in a simple way that you can understand, because there are so many things that it could make you somehow confused about how to use the principle of least action or Hamilton's principles, so we can have a very, very brief summary of fix what. So the summary of analytical mechanics. Including the Lagrangian and Hamiltonian. I think that one of the very, very important point is fixed. Fixed of what, right? You can fix the 2 endpoints of the path. That is one of the choice. That is Q0 and the Q is equal to 0. So that is the fixed, the 2 endpoints. And when you assume that 2 points, 2 endpoints are fixed, what can you derive? You can derive the Euler-Lagrange equation, right? I think it's very important that when you, after class, you should review everything that I have told you. And by calculating all of the things that I have derived in the class. If you do not do that, it'll be very easy for you to forget everything. So you should practice maybe many times, and then you can understand what does it mean, what is calculation, what is the procedure, and what is the important thing, and what is the assumption, and so on. Okay? And then you can understand the physical significance of what we have done during the calculations. It's very important. Okay, because after this class, we have a lot of calculations in the future. If you only follow, just listen to what I have told you, and we just see, oh, okay, the teacher is just write down so many things, it's good. And then after class, you do nothing. You will get nothing. Okay? So from this, you can derive the Euler Lagrange equations. Some people told me that the Euler should be pronounced as the Euler. Okay, Euler is the English pronunciation, but Euler is more French. Because you know, this guy is Lagrange is Italian French, and this guy is a Swiss. In Switzerland, we have the three languages, that is French, English, and Roman or something. Okay, so I prefer to pronounce that the Euler Lagrange equations. So that is like this, partial L, partial Q dot. Okay, and this guy is actually the P, that is the canonical momentum. So that is d over dtp, that is the P dot actually, is equal to partial L, partial Q. So that's one of the equations. And another possibility is that for the first case, you have many passes, right? You have many paths. You have the Q, that is T0 here, and that is T, this is T0. You can have this and that, you can have many things, that is Q, QT, Q1, and Q2 or something. But there is only one path that is physical. You fix these 2 points and let all of the possibilities to occur. And then you get this equation. And this equation indicates that there is only one solution to fit the actual physical path. That is this one. Okay, so fix 2 points and you get many paths. And then you, from many paths, you choose one. That one obeys the equation of this. Okay? You got what I see? Okay? Okay. And another possibility is like this, what I have told you, that you can fix the path, because the path has been fixed as the physical one. So that means when this is fixed, what will happen? It will happen that this equation is satisfied. Okay? And then you can have the two choices. The first one is to fix the Q0, and then you derive the P is equal to partial S, partial Q. And also you can fix Q. When you fix Q0, that means the Q, that point, is changeable. It's not a constant, but Q is in that path. It is changed, but it's in the physical path. Okay? And also, when you fix Q, that means the endpoint Q is fixed, but the starting point can be changed, but it is still in that path. Okay? Ready? Okay. And P0 is equal to partial S, partial Q0. And when you derive these two equations, you can derive the partial S, partial T is equal to minus QH, Q, partial S, partial Q. And this is the most important equation that is called Hamilton-Jacobi equation. And of course, then these two equations is also called the Hamilton-Jacobi equations. And from this derivation using the canonical transformations, by the generating functions of the type 1, you have verified that the two solutions coincide with each other completely. So that means the first principle, the principle of least action, is equivalent to the canonical transformations, or they do not disagree with each other, right? They are equivalent. So that's why that the canonical transformation that we have derived last time should be okay. That's equivalent to the Hamilton's principle, or the principle of the least actions. You get it? You got from the two approaches, two methods, and you get the same result. Okay? And now I think that you have derived, you have got the major points of what I've told you before. And so I can give you the canonical transformation using the type 1 generating function that is G1. And you can derive the Hamilton-Jacobi equation. And you, from H, Q, P, T, you just change to the K. That is the Q0, P0, T, which is equal to 0. And then you can get everything that you need. So this, I think that these relations are very important that you can get from the canonical transformations and the Hamilton's Jacobi equations. And at last, I would like to emphasize one more thing, that because the classical mechanics, or even the geometrical optics, has a bridge. That's a bridge. A bridge is what? This bridge is called the Hamilton-Jacobi equation. And then this is a bridge. From the Hamilton-Jacobi equations, you can connect the two things. One is classical mechanics, another one is quantum mechanics. And also the geometrical optics and wave optics. And I have told you last time that from this guy, you can find that the P is equal to the gradient of the action. And the action could be, in optics, it is called iconal in optics. And P is just like the K vector, that is the wave vector. You can just think about it. I don't think I have enough time to interpret the correspondence between the geometrical optics and wave optics using the Hamilton-Jacobi equations. And in the future, when we learn the quantum mechanics, we'll have approximation theory that is called the WKB theory. You can find in the WKB theory, you can find that from quantum mechanics, you can have some zeros, order approximation and corrections, and the first order or second order or something. You can find that the derivation from quantum mechanics is something like the classical mechanics, that is Hamilton-Jacobi equations. You can derive that. And when you see that, you can understand what I've told you today. Okay? Just keep in mind now, maybe you are not very comprehensive of what I have told you now, but keep in mind, and later, maybe several weeks later, you can understand what I have told you. Okay, so take the pictures and we can take a break. Okay, now let's go to the next topic, that is the classical electrodynamics. That is the survey and review of electrodynamics. It's abbreviated as the CED. The CED. And for electrodynamics, I think that the first thing is that we need to have some mathematical preparation. And the most important mathematical preparation, I think it's a vector analysis. Vector analysis includes the vector algebra and calculus. Yeah, vector algebra and vector calculus. For this, I think that I can draw a figure first. And this is the Cartesian coordinate. You have the three axes. That is the three-dimensional. It's a three-dimensional Euclidean space. This is a three-dimensional Euclidean space. So we have three axes. That is, or maybe x1, x2, and x3, right? So in this coordinate systems, you can have any kinds of the vectors. You can have, for example, you have the position, and position is the x1, e1, plus x2, e2, plus x3, e3. And e1, e2, e3 are three unit vectors of the axis, right? So we can write down this addition as the xi, ei. And this convention is called the Einstein convention. This is called the Einstein convention. It's like this. You can find the same index, that is I, and this is I. And when you face the same index, that means it is summed over of this index. And so this index is called the dummy index. Dummy index is like this. That means the index will be eliminated of the summation, right? And you will not have the index anymore. So that is dummy. It cannot speak. That means this. You understand? Okay. So this is called the Einstein convention. Because using this convention, many calculations will be made very simple. So we adopt this convention. And well, okay. And from this, we can derive that the E1 dot E2, that is the inner product or the dot product. We have several kinds of multiplications, several products, right? You have the inner product or the dot product, and also you have the cross product, or that is called the outer product. You can find that that's equal to 0. And also you have the E1 dot E3 or the E2 dot E3. That means because the inner product of the unit vector, for the unit vector, because they are perpendicular to each other, so the dot product is 0. right? And also you have the E1 dot E1 is equal to E2 dot E2, and is equal to E3 dot E3, that is equal to 0. That means the length of the unit vector is 1, is unity, right? So this equation, we can call this as the EI dot EJ is equal to the delta IJ. And delta IJ is called the Kronecker delta. This guy is called the Kronecker delta. It is a tensor. It is a symmetric tensor. Symmetric tensor. What does it mean? Symmetric tensor means that the delta Ij is equal to delta Ji. When you exchange the I and j, it keeps invariant. So that is called the symmetric tensor. Okay, and the delta is called the Kronecker delta. So that's a very important, very basic relations of the basis. This is the basis. So for the three-dimensional Euclidean space, we have 3 axes. So we have 3 unit vector. We have 3 bases, and each basis is perpendicular to the other basis. That means the x, E1, is perpendicular to E2, and also it is perpendicular to E3, and also E2 is perpendicular to E3 and E1. Okay, you got it? That's some very basic things. And also we can define another kind of very important, and this is called the inner product. Inner product. And also we call it the dot product. The dot product. In Chinese, it is like this. I think that you have learned that before, right? In mathematics or maybe in electromagnetic theory, probably. Another thing is that we have the cross product. And sometimes the outer product. Many names. That is, for example, EIEJ. So the cross product is defined by the right-hand rule. You have the EI here, EJ here, and then so you like this, and this is EK. That's the name of this rule is called the right-hand rule. Okay? So most of the time you should be very familiar with that. So you can find that from the 2 and 3, you got 1, right? So that is the right-hand rule for the cross product. And it is defined as what? As this, IJK, EK. So this is the definition of the cross product in terms of the Levi-Civita symbol. And this guy, epsilon IJK, is called the Levi-Civita tensor, or the Levi-Civita symbol. It is a tensor for the three-dimensional Euclidean space, but in some higher dimensional space, it could not be the tensor, it could be some other things. But here, in the three-dimensional Euclidean space, it is a tensor. So sometimes we call it as Levi-Civita symbol, sometimes called the Levi-Civita tensor. And what's that? What's this guy? Levi-Civita means its value is taken like this. Plus 1, that is positive 1, minus 1, or 0. It has 3 possibilities. The values of Levi-Civita has 3 possibilities. This is the even permutation. And odd permutation. And no order. And what is the even permutation? What is the odd permutation? What is no order? Even permutation is like this. 1, 2, 3. 1, 2, 3, that is even. Is equal to 2, 3, 1. And equal to 3, 1, 2. Is equal to 1. But if you have the 2, 1, 3, or 3, 2, 1, or 1, 3, 2, and many other possibilities, it is equal to minus 1. Okay? You got my meaning? You got? Yes. And what is the no order? 1, 1, 2, there is no order. Or 2, 1, 1, or 3, 3, 3, no order. So that's equal to 0. So that means if you want the Levi-Civita to be non-zero, you must have the different values for the indices. You cannot have the same even one. No. You must have the 3 index should be completely different. And then it could be sometimes minus 1, sometimes positive 1. But if you have 1, 1, 2, or 1, 2, 2, or 1, 3, 3, or something like that, no order, that is completely 0. Okay? You got this meaning? So, and this Levi-Civita is very important. So please keep in mind that this is a very frequently used tensor in the vector algebra and vector calculus in the future. So you should be very careful about that. Let me see that. So okay, let's see some properties. Properties of the Kronecker delta and Levi-Civita symbol. The properties. The first one is that delta ij is equal to delta ji. So that Kronecker delta is a symmetric tensor. And at the same time, Levi-Civita epsilon ijk is an anti-symmetric tensor. So the ijk is equal to the minus epsilon jik. So you can find ij and ji exchange. If you exchange the order of I and j, you got the minus. Okay, so that is the anti-symmetric. And the first thing that it is the symmetric and this is anti-symmetric. And so the third one is that if you have Fij is equal to Fji, so that means F is a symmetric tensor. So if you have Fij epsilon, if you have epsilon ijk Fij, this is anti-symmetric and this is symmetric, you will get it equal to 0. You can prove that. It is a homework. You can prove. It's very simple. You have the anti-symmetric tensor and you have a symmetric tensor together, and you have the contraction of the I and j, and then you get the result to be 0. That's a very important thing. Symmetric and anti-symmetric gives you nothing. Okay, take a break. We can practice, we can have some exercise now for several calculations. We have defined the inner product and the cross product. We'll write down here. So EI dot EJ is equal to delta IJ, right? And EI cross EJ is equal to the epsilon IJK EK. So this are some very, very basic relations between the bases. Okay. And now we can write down, and what is, if you have two vectors, for arbitrary two vectors, A and B, you have what? You have the A is equal to AI, EI, right? You have adopted the Einstein convention here, so that the I index is called the dummy index. And B is equal to BI, EI. So you can find that A dot B is equal to AI, EI dot BI of BJ, EJ. And then you can have the AI, BJ, EI dot EJ. And what's this? This is a chronic delta. So you have the AI, BJ, delta IJ. And then you can find that it is equal to AI, BI. So that is one of the properties of the chronic delta. It is a symmetric tensor here. So now you can find from here, you do not have any J index left, right? Okay, and what is A cross B? A cross B is AI, EI cross BI, no, BJ, EJ, right? And then you get AI, BJ. So that is, what's this? It is epsilon IJK, EK, AI, BJ, right? You can also write this like this, EK, epsilon KIJ, AI, BJ, right? And what's this? It is EK, A cross B, the K component, right? Remember that the epsilon IJK is equal to epsilon JKI is equal to the epsilon KIJ. So IJK here, we can write the KIJ like this. So we can find that the IJ is, they are I and J, I, J, J, they are the dummy index. And then you got no I or no J. The only thing left is K. And so this guy is the K component of the A cross B. And this is component, and this is the K's index, that is the basis K. You got it? So from this, you can find that the A cross B, the ith component of this vector is equal to the IJK, AJ, BK, right? J, J, K, K are dummy indices, and then the only index left is I. Okay, and the A dot B is equal to A I B I. So this equation, these two equations are very important. It will be used very frequently in the future when you have analyzed some calculations involving the vectors, including also you have the partial something, and also you use the same formula. Okay? So, for example, if you have the gradient of this guy, of scalar, you can have this, and it is equal to so in the future we'll just use this notation. The partial I means partial xi, and means the ith component of the gradient of the phi in the future for the simplification. Understand? Okay. And you can derive a very, very simple but very important relations of the gradient. And for any gradient of a scalar field, you find that it is a curve-free. Curve-free means that the curve of a gradient field is equal to 0. Can you prove that? It's very simple. This thing is very simple because we can just prove this is a vector, of course, and the ith component of that is like this. So that is epsilon ijk, and this guy is partial j, right? And this guy is partial k. I have told you that this j and k, if you exchange the j and k, you got the minus, because it is antisymmetric. And if you exchange these two guys, j and k here, you got no change because it is symmetric. Partial xj, partial xk, the same thing, right? So that is 0. So that's very important. When you learn the vector analysis, these relations are very important. For any kinds of gradient field, that means the gradient of any scalar potential, should be the curve-free, because the curve of any gradient field should be 0. Okay, so this is one of the properties of that. And the second thing is that the divergence-free. That means if you have a curve field, that is the curve field, that's the curve of a vector potential. That should be the divergence of this field should be equal to 0. And we can also prove this very easily. Is what? It's partial I, and this is I. So that is the curve of the vector potential A, the ith component of this one. This is partial I, and what's this? It is equal to I, j, k, partial j, a, k, right? So you have the epsilon I, j, k, partial I, partial j, a, k. So now you can take a look at this I and j, I and j. If you exchange the I and j in Levi-Civita, you got the minus. It's antisymmetric. But the partial I, partial j is equal to partial j, partial I. Right? Right? Yes. Okay, good. So that is equal to 0. So this, the curve-free relations and the divergence-free relations are very important two relations for the vector analysis. You should keep it in mind. And it's very easy to be proved using the Levi-Civita tensor and the antisymmetric and symmetric tensor if you have some contractions of the indices. You got? Okay, good. So next I want to introduce a very important formula, some very important formula. Okay, some important formula. Some useful formula. One formula is that the A dot B cross C is equal to what? You can have the cyclic exchange. You can have, it's the same as the B dot C A cross A, and it's equal to the C dot A cross B. You can prove this formula using all these rules that I have introduced before, which is very straightforward because the A dot B C here is equal to AI epsilon ijk bj ck. That is equal to epsilon ijk ai bj ck. So it's equal to epsilon jki. You can have the bj ck ai. You can find the ck ai with this. That is the j component of the C cross B, right? And then you got the cross C and A cross, and then you got result. You can have the inner product with the Bj. So this guy is equal to B C cross A. And similarly, you can get it is equal to the C dot A cross B. That is one of the solutions, proofs for this formula. But I think that there is a much more very imaginative interpretation for that. If you have a parallelepiped volume of this guy, if you have this, like this, because this is A and this is B and this is C. You can find that the B cross C has the absolute value for that is the area of this plane, right? And then if you have the A dot this B cross C, you got the volume of this parallelepiped. This is called parallelepiped. So A dot B cross C, the geometric meaning of the A dot B cross C is the volume. Is the volume of the parallelepiped. And similarly, B dot C cross A and C dot A cross B has the same meaning as the A dot B cross C. So that is the volume of this parallelepiped, because you have the A, B, and C. You have three vectors. Okay, so I think that this analysis using the geometric imaginations is much better for you to understand all of the things of the formulas. Is that? Okay. So this is one of the important formula. So let's see another, I think there is also some very important formula. You can also find that what is ijk is equal to ei dot ej cross ek. By the definition, very original definition, you can prove this. The Levi-Civita is equal to the ei dot ej cross ek. So it can be written as a determinant. It is 1i, 1j, and 1k. And you have the 2i, 3i, you have the 2j, 3j, and delta 2k, delta 3k. You can have this definition of. And further, you can have the epsilon I, j, k, and l, m, n. If you have two Levi-Civita symbols, to have the product of that, and you get the determinant, which is delta, 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 delta. That is I, j, k, I, j, k, I, j, k. That is L, M, N, L, M, N, L, M, N. You can find that. It's equal to this determinant. And after this, you can derive a more useful formula that is very frequently used. That is ijk. If you have KLM, you have the same index here, so that is the Einstein convention. You will not have any k left. And this equation is very important. That is IL Jm minus Im Jl. This formula is very frequently used in the future, so you should be very familiar with this. Because you will have a lot of, you have two vectors. One of the vectors is the cross of something, and another one is also the cross of something. And then they have some inner product, and you should, and then you need this formula. This is a very frequently used. So that is frequently used. Okay, so should pay more attention about it. And using this formula, you can prove a lot of very useful other formulas of the vector calculus. The vector calculus of the formulas. For example, if you have two scalars, you have it is equal to u gradient v plus so that's a generalization of the Leibniz formula in a calculus to the vector analysis. And also we have a much more complicated formula, that is if you have the gradient of a dot b. This is very complicated, but you can prove by using what I have told you. You can prove this formula, that is equal to a cross nabla cross b and plus the a b and plus b cross the curl of a and plus the b dot nabla a. And this equation, this formula is also very frequently used in the electromagnetic theory. But maybe you need to verify or prove this formula to be valid. It's very, and also the next one is the divergence. The divergence of two vectors cross product is like this, which is equal to the B dot the curl of A minus the A dot the curl of B. This formula is also very frequently used. And also we have the curl of the A cross B, and this equal to plus minus and minus. Okay, this formula. I just listed some very important and very frequently used formulas. And this guy, formula, the nabla cross A. So that is the curl of another curl of the vector potential. And this formula is so frequently used that every day, maybe in the future, when you encounter anything that related to the electromagnetic field. So this formula, you should be very, very familiar with that. You should practice, you should prove this by yourself. This formula is very important. So, and also we have proved that this guy is equal to 0, and so that means the gradient field has no curl, and the curl field has no divergence. Okay, so I think that these formulas are the most frequently used and most important formula that you may need in the calculations related to the electromagnetic field in the future. Okay, and I think that I should mention two more formulas that in here. One is that, oh, I need to have more space. One is this guy. What's that? What is R? R is equal to this. R is equal to, it's a square root of the x1 square plus x2 square plus x3 square. So that is the length of the vector. That is R. And what is R? What is the gradient of 1 over R? And this formula is also very frequently used because the 1 over R, if this is a scalar potential, that means the force related to this potential should be something like, it's called the inverse square force, like the Coulomb force or the gravitation. That's the same, that's the inverse square law, that's a central force. And that is equal to the minus 1, this is vector x over r cubed. And this formula are also very frequently used. And this is equal to this. It's 4 pi delta x. That is the delta function in the three-dimensional space. So keep in mind this, that the nabla square, that's a Laplace. The Laplacian of the 1 over r is equal to the 4 pi delta x. And this formula is also very frequently used. We will not prove all these formulas now because we have no time to do that. But keep in mind that's something that is very important. And I would like to mention two more vectors that is very important. And I think that maybe most of you have not yet met such a vector that is called the Laplace rank length vector. And in classical electrodynamics, we have, or the classical mechanics, we have the definition of the Laplace rank length vector, LRL vector, is defined as it's equal to the P cross L minus M K X over R. Actually, the X vector X over R is a unit vector of the X vector direction, right? And M is the mass of that particle. And K is something related to the properties of the force. The force could be a Coulomb force, and K is equal to ZE. Z is the atomic number, and E is the electric charge. And K can also be the GMM. G is the gravitation universal constant. And you have the capital M and small m. That is one of the big mass and the small mass. So anyway, so this K is a parameter that is related to the type of the force. Okay? It could be the Coulomb force and also the gravitation. And another thing is that quantum mechanics. In quantum mechanics, we also have the LRL vector, and the definition is different. And in quantum mechanics, the A is an operator, and so it should be Hermitian. I just write down the expressions of the A vector, and I will introduce and give the explanations later when we encounter the SO4 group in the future. But now I just write down it is defined as the P cross L, and P is the momentum and L is the angular momentum minus L cross P. And the other thing is the same. But X is also an operator now. Okay? So this vector, LRL vector, or sometimes I just call it length vector, is very important because the conservation of this vector is related to some symmetry in the four-dimensional space, four-dimensional Euclidean space, and it is related to some, we have the principal quantum number, and we have the degeneracy of the n square that is related to the principal quantum number, and that's conservation, and degeneracy is related to this vector. So I just mentioned here. Okay, and now I think that I should introduce something about the electrodynamics. Electrodynamics, because we don't have much time, so I just introduce some very simple things about the electrodynamics. The classical. The classical electrodynamics that is involved in the quantum mechanics is the most important thing that involved in quantum mechanics, I think, is the multiple expansion of the electron electromagnetic. And we have the scalar potential that is equal to the integral of the charge density and you have the x minus x prime cube. Oh, I'm sorry, made some mistakes. So this is a scalar potential. And also we have the vector potential. It is defined as this. Before introducing further, I would like to mention one important theorem. One important theorem that is called the Helmholtz theorem. Helmholtz theorem of decomposition of vectors. What's that theorem? The theorem told us that for any vectors f, if the vector is continuous and differentiable, then the f can be decomposed as the two components. One is like this, another one is like this. So this guy is called the longitudinal. And it satisfies the curl of that is equal to 0. And also, this is called the transverse field. Divergence of this transverse field is equal to 0. So any kinds of vectors can be decomposed into two parts. One is longitudinal, that curl is equal to 0. Another one is transverse, and divergence is equal to 0. So that's why we only have 4 equations in Maxwell equations in electromagnetic field, right? We have 2 divergence equations, we have 2 curl equations. And that's enough because we have the curl and the divergence expressions for the field of the electric field and the magnetic field. So if we do not have the Helmholtz theorem, we will not know that the 2 divergence and 2 curl equations are sufficient for the electromagnetic field. But we have the theorem, and then we just have the 2 plus 2 equation. Altogether, we have 4 equations. That's enough. So you see what I mean? Okay, it's good. Okay. And I would like to draw a figure here. And in the electromagnetic field theory, we have such a, if we have, this is a zone that we have maybe some charge, and also we have some electric current here. And this point is called the x prime. If we have this volume is called the v prime. If we have the v prime, x prime, that means that is the source. We use the prime to identify that is the source point. And also we have the v or x or something, that means that is the point of the field. So in this point, we have some source, the source of charge, the source of current, electric current, and then it can produce what? The electric field or the magnetic field, maybe here. This is an X, right? So this is X prime and this is X minus X prime. And this is X point. So the source point here produces the electromagnetic field in this point. And the field is related to the relative distance between these 2 points. And for the scalar potential, it is proportional to the electric charge density. And for the vector potential, it is related to the electric current density. Okay? And we know that the E, that is an electric field, that is equal to the minus gradient phi minus 1 over c partial A partial t. And B is completely is a transverse field because it is equal to the curl of the vector potential. Okay, so that's all. And we can expand the scalar and vector potentials using the Taylor expansion because we have the 1 over absolute value of the x minus x prime, right? Because we know that the x minus x prime is equal to something like this. Something like this, right? This is a Taylor series, Taylor expansion. Because we know that the x prime, the absolute value of x prime is much less than the distance of the x. And x, the absolute value of x is equal to r. So we can expand like this. And so we can write down the phi is equal to phi 0 plus phi 1 plus phi 2 or something. And A is equal to A 0 plus A1 plus A2 something. And from this we can derive the E is equal to E0 plus E1 plus E2. And from this we can derive the B is equal to the B0 plus B1 plus something. And the E1 is called the electric dipole. And the E2 is called the electric quadrupole. And B1 is called the magnetic dipole. But normally we just ignore the dipole for the electromagnetic field. We just say that we have some magnetic moment. But magnetic moment means the moment of magnetic dipole. Okay? We don't have enough space. Oh. Okay, we have a very small space here. Therefore, for the interaction between the outer exterior field, that is electric field or the magnetic field. For the electric field, you have that is equal to this. It's equal to the minus d dot E. And this is the exterior electric field. And this D is the electric dipole moment. So that is E. And for the magnetic, so this is also the exterior magnetic field. And this is called the magnetic dipole moment. This is the electric dipole corresponding to this. And this is the magnetic dipole corresponding to this. And also sometimes you need to have some more expansions. You may have interactions between the electric quadrupole interactions with the electric field. And then it is, you have E something, that is the tensor. Okay, so that's some very important and simple things. So I think that I don't have any space left. So probably you take the pictures about the blackboard, and then we may have some space. I may tell you something more. I think that we have 5 minutes. I want to emphasize something. We notice that the UE, we can have the minus D, E, plus, we have some quadrupole probably. So that is the electric dipole interaction. With the exterior electric field. And this is the electric quadrupole interaction with the exterior electric field. So you find that for the quadratic interactions, you have the tensor. It's a dialectic of the electric field. But for the dipole interaction, you have only one E here. And this guy can be calculated using some way. You can. We just have the expansion, and you see that the D is related to some expansion coefficients of that. So that is the electric field interactions with the dipole and with the quadrupole. And also we have the M. And that is the magnetic dipole moment interaction with the exterior magnetic field. And M is called the magnetic dipole. And the dipole is very usually ignored moment. And we can, using the classical electrodynamics, we can calculate, we can get the result of M. And it is something like so you can find that this magnetic moment derived from the classical electrodynamics has completely the same expression as the moment, the magnetic moment expressions in quantum mechanics. So this expression is derived in classical electrodynamics. If you calculate step by step using the multiple expansion, you can derive this result. So this is not derived from quantum mechanics, but we'll use it. But of course, in quantum mechanics, you can derive the same thing. But this is only valid for the orbital angular momentum because it is related to the angular momentum. But L here, L is equal to x cross p. So that is the orbital. That's the orbital angular momentum. And this term is only used in quantum mechanics. In classical mechanics, we have only this kind of angular momentum. We don't have any spins in classical mechanics. But in quantum mechanics, we have the orbital angular momentum, and also we have the spin angular momentum. And for the spin angular momentum, you will not have this coefficient. You will not have the 2 here. For the spin angular momentum, you have only the M, the moment, the magnetic moment, the intrinsic moment or something is equal to the QS over M. You don't have the 2 here anymore in quantum mechanics. So, okay, I think that I have introduced so many things that is in classical electrodynamics, and that is related to the quantum mechanics. And I have finished all of the things, classical mechanics, classical electrodynamics, and many knowledge. And I think that's a good way for us to have a survey and review. And during these 2 weeks, you have a lot of time to review all of you have learned before in the classical mechanics and electrodynamics. And because you have a National Day holidays, so you can have more time to review and accomplish all of your homework. And that will be a very good background basis for learning in the advanced quantum mechanics in the future. Okay, that's good.